This is the third module in 6 about databases. In this module, we will be talking about relational databases. You will remember from the previous module, when we talked about data models, that we talked about the relational data model, how data can be organized in a set of tables with rows and columns, or relations, attributes, and domains to give them their formal titles. And a relational database is a database which uses the relational model as the means to structure its data. There are a number of features of a relational database that I want to talk about. First of all, things that a relational database gives you that are very useful for the management, administration of data in a database. One of the most important for the purposes of a relational database is the notion of a transaction. A transaction is an atomic sequence of actions, whether it's read or write, in the database. And transactions in a database have to be executed completely by definition, and they must leave a database in a consistent state. You can't have a transaction which leaves the database in a dangerous state. That would not be allowed. If the transaction should fail or abort midway, the database rolls back to an initial consistent state. Now, you don't need to worry about this yourself because the database management system in the relational database is taking care of this for you. But it's nice to know that should a particular transaction fail or crash for some reason, when you're using a relational database, the data is not going to be compromised in any way because the DBMS is going to go back to a safe position. This is one of the advantages of using a DBMS as opposed to just working programmatically with your data. If you were doing a calculation on your data and you suddenly collapsed or crashed, you may find that your data is corrupted. The hope is that with a relational database, that is less likely to happen. An example of a transaction is, for example, let me say I'm going to authorize PayPal to pay $100 for the eBay purchase I just made. In terms of the steps of the transaction, it has to debit my account $100 and it has to credit the seller's account $100. If the transaction fails halfway through, either my account has not been debited and the seller's account may have already been accredited, or the verse may be true that he has the money, I don't have the money, or I don't have the money and he has the money. That would not be good. It would leave us in a dangerous state. Either I don't have money or he hasn't got the money, and so we would need to roll back to an initial state where the money was in my account again. So that's an example of a financial transaction, but you can imagine the same thing happening with data when you're doing a data operation in a relational database. By definition, therefore, a database transaction is what's called ACID, which is an acronym that stands for it's atomic. So either the transaction completes or nothing happens. You don't get half the transaction occurring. The database transaction is consistent. There are no integrity constraints violated. What that means is that I may have some constraints on the type of data or the format of data that is allowed in one of my data columns, or connections between different data tables, different relations, and none of those are violated, none of those are compromised by the database transaction. A transaction is isolated in the sense that it has no impact on any other transaction that's going on. And finally, the database transaction is durable. Once a database transaction has been committed, the effects of it are permanent and persistent. You're not going to fall back to a former position at some later stage. So that is ACID, which you talk about with database transactions. One issue with relational databases is the notion of concurrency. What happens if I have multiple transactions going on at the same time, coming from different clients? The database management system ensures that those interleave very nicely and that they don't cause inconsistencies in the data that they are working with. What it will do is the DBMS will analyze the transaction set that is currently being considered, and it will convert that into a new set that can be executed sequentially. Again, this is something that you don't need to do yourself. It is a benefit of the relational database system that you're using. One way that it can do this is that before reading or writing an object in the database, each transaction waits for a lock on the object, and when the transaction is finished, it releases all its locks. And in that way, a data value that it may be using can't be compromised by another transaction. You isolate the data that it may be working with. And since you're only having a set of logically meaningful sequence of transactions, that doesn't cause any inconsistencies. Locks, just previously mentioned, the database management system can set and hold multiple locks simultaneously on different levels of the physical data structure. One of the advantages of a DBMS is that it allows you to control the access or the operations on different individual pieces of data or groups of data in ways that are sensible. There's multiple granularity. For example, at a row level within a table, you could lock that, a basic data block, a page, a whole set of pages, or even an entire table. You can have a read lock or a write lock on, or something like that. There are different types of locks, exclusive locks versus shared locks, that the access to the data is limited to one person, or it could be shared between a group of named individuals or named actors. You can have optimistic versus pessimistic locks, which behave in different ways depending on the situation being considered. So there are a variety of locks that the DBMS is working with, but it's worth being aware of those, because sometimes you may require low-level access to try and understand a problem you may be having with your database, and it may be related to data access and to locking. A relational database will have a set of logs where it writes down, keeps track of all the transactions that are occurring with the relational database. This ensures the atomicity of transactions, the A part of the ACID, that there is a complete set. And it's useful should your database unfortunately crash. Any partially executed transactions can be undone using the log. You'll remember that the atomicity means that the transaction either is fully complete or doesn't happen at all. Obviously, if you're halfway through, you would violate that, but because you have a log of what operations have been carried out as part of a transaction, you can reverse those actions to take you back to a clean, uncompromised state, uncorrupted state. Typically, a log record will have some sort of header which involves a transaction ID and a timestamp. It will have an ID of the item in the relational database that you're working with, and may say what the type of the transaction is, and then it may be an old and a new value. So those are the sorts of things that you have in log records, should you need to go through a log record to understand what's going on possibly. Data, obviously, if you have a lot of data, your performance, you may find, is particularly slow in a relational database, and there may be more efficient ways of breaking your data up. This may be particularly if you have more data than you can fit on a single machine. So you have a cluster of machines which are your relational database system. There may be ways of partitioning the data which are meaningful. There are different types of partitioning schemes. There's a horizontal partitioning where you have different rows, and you put different rows in different tables, potentially on different machines, different hosts. Or you can have one big table which has very many data in it, and you want to do vertical partitioning, that you break it up by columns, and you put different columns into different tables. That's part of a thing called normalization of a relational database, and I'll talk about that in a minute. You may partition according to range, where those rows which have values in a particular column are within a certain range going into one table on one machine, and those in another range, those values on another machine. A list, instead of specifying a range, you may have something which has a particular data value which has a finite number of allowed values, and you could have a list where the values in the particular column match a subset of that, and you use that for your partitioning. Or you may have a more general hash function which returns a particular value depending on the value of particular columns in a row, and the partitioning is done on the basis of that, according to the value of the function. Finally, I'll talk about, mention database normalization, relational database normalization. These were a set of rules that Cobb, who came up with the relational database model, devised what are called the normal forms. I think there are 12 normal forms in all, but the ones that really only make sense are the first 3, or the ones that are most commonly used. The idea here is that these ways of normalizing the relational database make it particularly efficient and are particularly sensible or logical from a relational data model perspective. In the first normal form, you will find that there are no repeating elements in a database or a group of elements. Each has a unique key, and also that you have no nullable columns, that each column actually has a value in it. In the second normal form, no columns in a table are dependent on only part of the key. So, for example, if you had a column of a table of stars, you may have 3 columns which might be the star name, the constellation that the star is in, and the area of sky. And obviously there's a dependency there between one or more of those columns, which you would remove if you were normalizing your database according to second normal form. In third normal form, you have no columns dependent on any other non-key columns. In that case, you would just have star name, magnitude, and flux, for example, but magnitude and flux are related to each other. One is the log of the other, and so therefore you would remove one of those if you were normalizing your database according to third normal form. These are not mandatory requirements when you construct a database or a relational database, use a relational database, but it is generally considered good practice to consider at least one of the normal forms to use for the purposes of keeping your data organized in a clean fashion in the relational database. And that is the end of this talk.